All right, the next example, example 7. Again, analyze the critical points of this function. So, go ahead and start by taking a first derivative to get 1 minus x to the 2/3. Oops, that's just the original function. What should we do here? This should be 2/3 times that. 2/3 minus 1 is negative 1/3 times the derivative of the inside, which is negative 1. And if we go ahead and rewrite this, this is negative 2 over 3 times the cube root of 1 minus x. So now let's go ahead and notice here that for the original function, right here, domain is all real numbers. Why is that? Well, because we're not taking the square root, we're taking a cube root. We are first squaring this, and then we are cube rooting it. That's what the 2/3 means. So, only even roots do we have to worry about a limited domain. For a cube root, there's no issue with taking the cube root of a negative, so the domain here is all real numbers. However, when we take the first derivative, this negative exponent that appears from the power rule means that this term actually lives in the denominator, which means that this first derivative does not exist at x equals 1, because we'll get 0 in the bottom, and then we'll obtain division by 0. So what's important here is when you realize or see that the first derivative does not exist at some location, you have to make sure that this location at which it does not exist does belong to the domain of the original function. It's only when it belongs to the domain of the original function but breaks the first derivative. In other words, it's removed from the domain in the derivative even though it belongs to the domain of the original function. That is when we can say that this x equals 1 is in fact a critical point. If it so happened to be the case that x equals 1 was not in the domain of this function, then it not being in the domain of the first derivative doesn't make it a critical point. It's just nothing. So it has to work for the original but break the first. So we can say dne at x equals 1, so we can say a critical point. Now we have to see, when does the first derivative equal 0? Well, the only time that a fraction, so right, we got a fraction here, the only way a fraction equals 0 is if the top number equals 0. Well, negative 2, let's say, negative 2 does not equal 0. So what we're going to go ahead and say here is that actually this does not equal 0. So the only source of critical points are from the derivative not existing. There are no contribution of critical points from where the first derivative equals 0, since the first derivative never equals 0. So there's one critical point. So we can go ahead and set up our sign graph for the first derivative. So the real number line, negative infinity to infinity. We list our lone critical point, and we'll go ahead and just say that the first derivative does not exist at that point. So now we're going to take sample points. We can go ahead and do f prime of 0. That's a convenient number. And we can also use f prime of 2. When we do that, f prime of 0 will end up getting negative, and f prime of 2 will end up getting positive. So we get negative, positive, which means here we get something like that. Again, we only get a nice rounded bottom to our graph if the derivative exists. That means it actually has a horizontal tangent. If the first derivative does not exist at this point, it means that the tangent line can't be defined, which means that the left-hand slope does not equal the right-hand slope, which means we have some sort of cusp. So, regardless, this is still a local minimum at that location. So we can say there is a local minimum at the critical point x equals 1. There we go. We've analyzed that critical point.